Far below the surface of the Pacific Ocean lies a place so deep that sunlight has never touched it. The Mariana Trench, stretching nearly 11 kilometers beneath the waves, is the lowest point on Earth, a scar in the planet's crust where the ocean presses down with unimaginable pressure. It is a realm almost entirely unexplored, a place where technology struggles to keep up with the environment. In 1997, scientists listening quietly in these depths recorded something extraordinary, a sound unlike anything they had heard before, later nicknamed the biotwang. The discovery began with hydrophones, specialized underwater microphones designed to capture sounds in the deep sea. Researchers working on the National Oceanic and Atmospheric Administration's NOAA Pacific Deep Sea Monitoring Program had set up these instruments to track seismic activity and monitor marine life. Most of the recordings were familiar: low rumbles from earthquakes, clicks and whistles from whales and other deep-sea creatures, the occasional distant rumble of submarine volcanoes. But one sound stood apart. It was sharp, resonant, and unlike any known marine noise, bouncing through the trench in strange patterns. The sound was dubbed the biotwang because of its unusual tonal quality, reminiscent of a stretched string or a plucked instrument echoing through a cavern. Its source was initially unknown. Researchers pored over data, trying to determine whether it was biological, geological, or perhaps even artificial. The problem, as always in the Mariana Trench, was distance and pressure. Instruments can survive only so long. Direct observation of the seafloor is extremely limited, and the environment itself distorts sound in ways scientists still struggle to model. Early speculation ranged widely. Some wondered if unknown marine creatures were producing the sound. The depths of the trench are home to species barely studied, organisms adapted to crushing pressure, perpetual darkness, and near-freezing temperatures. Giant squid, deep-sea fish, or undiscovered cephalopods were all proposed as possibilities. Others suggested geological sources: shifting tectonic plates, underwater landslides, or ice quakes from the melting polar regions transmitting vibrations across vast distances. For a time, the biotwang became a symbol of mystery, a deep-sea enigma that seemed to suggest life, or processes, we had barely begun to understand. Scientific investigation moved carefully, using repeated observations. Researchers compared the sound with known whale calls, fish noises, and seismic data. They mapped the trench and its surrounding waters, correlating the occurrence of the biotwang with environmental changes. Patterns emerged. The sound was not constant. It appeared sporadically, sometimes coinciding with seismic tremors or movements of deep water currents. The variability made it harder to pinpoint a single source, leaving the door open for both natural and biological explanations. Some studies suggested that ice quakes, fractures in drifting polar ice, could send low-frequency vibrations across the ocean floor, even reaching the Mariana Trench. These events produce sharp, high-energy sounds as ice shifts, cracks, and collides, generating echoes that travel through the dense, cold water. This theory could account for some recordings of the biotwang, especially those that match times of seasonal ice movement. Yet it did not explain all instances. The trench remained a place where anomalies persisted. Marine life also offered plausible explanations. Certain species of deep-sea fish and invertebrates produce sounds for communication, mating, or territorial purposes. The Mariana Trench is home to many unknown creatures, and some scientists theorize that the biotwang could be a form of biological signaling, a sound designed to travel long distances in extreme depths. Unlike whales or dolphins, these animals would rely on low-frequency vibrations, since higher frequencies dissipate too quickly in such dense water. The idea is compelling, but direct evidence is scarce. No species has yet been positively identified as the source. Adding to the intrigue, the trench is a dynamic geological environment. Subduction zones, where the Pacific Plate dives beneath the Mariana Plate, create constant stress. Small quakes, rock collapses, and shifts in sediment occur regularly. These movements can produce sharp, echoing noises that hydrophones detect. Scientists using high-resolution seismic monitoring have recorded bursts of energy strikingly similar to the biotwang, lending weight to the theory that at least some sounds are geological in origin. Still, the overlap with biological possibilities keeps the debate open. The recording and analysis of the biotwang highlighted both the power and limitations of modern technology. Hydrophones can listen, cameras can film, and submersibles can descend, but only for short periods. The extreme pressure at the trench floor, over 1,000 times the atmospheric pressure at sea level, makes sustained observation nearly impossible. Even robotic probes face crushing conditions that limit data collection. Every sound captured carries both insight and frustration. It is a clue but not a complete answer. Despite decades of research, unanswered questions remain. The Mariana Trench continues to challenge our understanding of deep-sea acoustics, biology, and geology. Sounds like the biotwang remind us that Earth's oceans are not empty voids, but complex, interconnected systems with mysteries that resist easy explanation. Each recording invites curiosity and speculation, encouraging scientists to keep listening, mapping, and exploring. As the years passed, researchers refined their methods for studying the Mariana Trench's mysterious sounds. Hydrophones became more sensitive, able to pick up vibrations that would have been drowned out by background noise in earlier recordings. Arrays of these underwater microphones were deployed at strategic points, creating a network capable of triangulating sound sources. This allowed scientists not only to hear the biotwang, but also to begin mapping its likely origin and behavior over time. One major breakthrough came when patterns started to emerge. Some recordings of the biotwang coincided with seismic activity along the trench, supporting the idea that shifts in the Earth's crust were producing the sounds. These tectonic pulses occurred sporadically, often accompanied by subtle tremors detected by ocean-bottom seismometers. When researchers compared multiple datasets, they realized that certain deep Earth events could transmit energy across vast distances underwater, producing the sharp, echoing tones that first captivated scientists. Yet not every sound aligned with seismic records. Some bursts of noise were observed during periods of geological calm, suggesting a biological component. Deep-sea marine life produces noises in ways that are still poorly understood. Certain species of fish, squid, and even invertebrates generate low-frequency sounds for communication, hunting, or mating. At extreme depths, sound travels farther and differently than in shallower water, meaning noises produced by a small creature could be heard kilometers away. Some scientists hypothesized that the biotwang might be a type of long-range signal, designed to carry through the trench's dense waters, although no creature has yet been directly linked to the sound. Technology also expanded in the form of submersibles and remotely operated vehicles, ROVs. These machines, capable of descending several kilometers, allowed direct visual observation of parts of the trench floor. Cameras and sonar mapped previously uncharted features, including deep chasms, hydrothermal vents, and unusual rock formations. Occasionally, sounds recorded by hydrophones could be compared with the terrain below, providing context. For instance, shifting sediment along steep trench walls or the collapse of small underwater cliffs can produce echoes that mimic the tonal qualities of the biotwang. Despite these advances, the trench remains largely inaccessible. Pressure at the bottom exceeds 1,000 atmospheres, temperatures hover just above freezing, and the absence of sunlight makes traditional navigation and observation difficult. Robotic missions can last only a few hours before returning to the surface, leaving long periods unmonitored. As a result, scientists often rely on acoustic data as their primary window into this hidden world. Every sound captured carries both excitement and limitation. It tells us something but never the full story. The Mariana Trench sounds also sparked public fascination. Documentaries and articles portrayed the biotwang as one of the ocean's last great mysteries, drawing comparisons to lost cities, alien signals, or unknown giant creatures. While sensational headlines sometimes overstated the mystery, they helped highlight the real scientific challenge. Exploring the deepest, most extreme parts of our planet is still an emerging frontier. It reminded the world that the ocean's deepest layers are not fully mapped, and that mysteries persist even in an age of satellites and submersibles. Interestingly, the study of these sounds has wider implications. Understanding how low-frequency vibrations travel through deep water informs marine navigation, submarine communication, and even earthquake monitoring. It also provides insight into how deep-sea ecosystems function. Many species depend on sound for survival, and the extreme acoustics of the trench create a unique environment for life to evolve strategies that humans are only beginning to understand. Yet, for all this research, unanswered questions remain. Why do some sounds recur at irregular intervals? Could multiple sources, biological and geological, overlap to produce the same tonal effect? Are there deeper processes at play that we cannot yet detect? Each recording adds a piece to the puzzle, but the trench resists full explanation, reminding scientists that exploration is as much about patience and observation as it is about discovery. Even with decades of research, the Mariana Trench sounds continue to spark debate among scientists. One reason is the trench's sheer inaccessibility. At nearly 11 kilometers deep, direct observation is rare. Researchers must rely on indirect evidence: hydrophones that detect vibrations, ROVs that film small sections, and sediment analysis that hints at geological activity. Because of these limits, multiple explanations for the biotwang remain plausible, and the mystery persists in a measured, scientific way rather than a dramatic one. Some scientists maintain that the sound is primarily geological. Subduction zones in the trench constantly shift, producing microearthquakes and minor landslides. The trench floor itself is uneven with walls, ridges, and sediment flows. When portions of the seafloor collapse or shift suddenly, they generate acoustic pulses that can carry for tens of kilometers. These events, sometimes called deep earthquakes or trench quakes, could explain many of the biotwang recordings. Supporting this, patterns of the sound often coincide with seismic data, suggesting at least a partial geological origin. Others emphasize the possibility of biological sources. Life in the trench is extreme but abundant. Microbes thrive near hydrothermal vents, while larger species, from deep-sea fish to gelatinous invertebrates, use sound to navigate and communicate. The biotwang's tonal structure is unusual but not impossible for marine life. Low-frequency sounds travel farther in water, making them ideal for long-range communication in darkness. While no specific creature has been identified, scientists speculate that unknown species may be producing noises designed to propagate efficiently in these extreme conditions. Some researchers suggest that both explanations may overlap. Geological activity could trigger a response from deep-sea organisms, creating a combined acoustic signature. For example, a landslide might disturb sediment, producing a sharp sound, while startled animals respond, creating secondary vibrations. In a place as complex and underexplored as the Mariana Trench, layered explanations are entirely plausible. This duality makes the biotwang a fascinating study, not only for oceanography but also for marine biology. The public fascination with the trench sounds has been equally complex. Documentaries, podcasts, and online articles often describe the biotwang with dramatic language, highlighting the unknown or comparing it to alien signals. While sensationalized, this attention has encouraged funding and further study. More hydrophones have been deployed and longer-term monitoring programs have been established. These efforts have created one of the most detailed acoustic records of any part of the deep ocean, even if the exact source of every sound remains elusive. Technological advances continue to shape our understanding. Modern hydrophones can capture broader frequency ranges and record with higher resolution. Autonomous vehicles now carry sensors to the deepest trenches, collecting environmental data alongside sound recordings. Future missions may combine 3D mapping with acoustic analysis, potentially allowing scientists to match specific sounds to geological events or marine life in real time. The promise of this research keeps the biotwang in the spotlight of deep-sea exploration. At its core, the Mariana Trench sounds illustrate a fundamental truth about the ocean: the deeper we go, the less we know. Even in an age of satellites, submersibles, and advanced sensors, the trench holds surprises. The biotwang is a reminder that natural processes can produce phenomena that challenge understanding, and that life can adapt in ways humans have yet to fully comprehend. It is a mystery grounded in data, yet rich in possibility. The Mariana Trench sounds are more than just a curiosity, They are a window into a world largely hidden from human eyes. By studying these noises, scientists gain insight into how the planet's crust behaves under extreme pressure, how sediments shift over time, and how life adapts to one of Earth's harshest environments. The biotwang, along with other recordings, serves as a natural experiment, showing us that sound travels differently in dense, cold water, and that even tiny vibrations can reveal large-scale processes happening miles below the surface. One of the most important lessons comes from the biological side. The trench is home to organisms that have evolved to survive crushing pressure, near-freezing temperatures, and total darkness. Many rely on sound to detect predators, locate food, or communicate with mates. Understanding these acoustic signals allows scientists to map activity, behavior, and even population densities in places too remote to reach physically. Each unusual recording, whether a sharp pulse or a sustained hum, adds to the knowledge of life at the extreme edge of habitability. Geology and biology also intersect in surprising ways. Sediment slides and underwater quakes can create vibrations that ripple through the trench, and these disturbances may trigger responses from deep-sea life. Conversely, large numbers of animals moving in unison could influence sediment patterns, subtly shifting the seafloor over long periods. The biotwang may not be a single phenomenon, but rather a symphony of interactions between Earth and its living systems, layered and overlapping in ways modern science is just beginning to interpret. Even as technology advances, there are limits. Hydrophones can only record what passes through their immediate area. ROVs and autonomous vehicles are limited by battery life, communication constraints, and extreme pressure. For every sound captured, there are countless others lost to the depths. The trench is a reminder of how much of our planet remains unexplored, and how mystery can coexist with careful scientific observation. The public fascination with these sounds highlights another dimension. While headlines often focus on the exotic or the unknown, the reality is equally compelling. The Mariana Trench is a living laboratory where geology and biology meet under extreme conditions. Every recording of the biotwang challenges assumptions, prompting questions about life's resilience, the planet's dynamic systems, and how humans study worlds we cannot easily reach. This balance between awe and evidence is what makes the trench such a powerful symbol of scientific exploration. The Mariana Trench sounds also underscore the importance of patience in research. Progress is slow, incremental, and often frustrating, but each discovery, whether confirming a geological source or identifying a possible biological one, adds to a broader understanding of deep-sea dynamics. Scientists continue to refine models, improve sensors, and develop new methods to study the trench. Each year brings slightly more clarity, yet the full picture remains just out of reach, preserving a sense of wonder and curiosity. Ultimately, the biotwang and other unexplained noises remind us that Earth's oceans are far from fully understood. Even in a time of satellites, robotics, and advanced imaging, there are places on our planet where the familiar rules of human experience, light, sound, pressure, operate differently. The Mariana Trench is one of those places where mystery and knowledge coexist, encouraging both humility and fascination. As we reflect on these sounds, it becomes clear that the Mariana Trench is not only a location for recording unusual noises, but a testament to the unseen complexity of our world. Its unexplained sounds, layered with geological shifts and the life forms that call it home, tell a story of resilience, change, and ongoing discovery. The trench remains a frontier, inviting future generations of scientists to listen, explore, and slowly unravel its hidden rhythms.